Welcome to Notes 8.5, Central Skill H5, or the form of a complex number. Recall that a complex number has the form a plus bi, where I is the square root of -1. We can express these in terms that are very similar to polar grid plotting. To begin with, we have the complex plane. When we plot on the complex plane, it looks very rectangular, and so this is going to bear many similarities to the previous notes. Our ordered pair is simply a comma b. When we plot a point, we take the real component as the horizontal coordinate, and we take the imaginary component as the vertical component. Take a moment and try the other ones. Pause if you'd like, and make sure you get this right. We can talk about the absolute value of a complex number. It's simply defined as the distance from the origin. We still use absolute value bars, and we compute this using the distance formula or the Pythagorean theorem. For example, here's how to find the absolute value of two different complex numbers. There's a shortcut to number 3. See if you can spot it before I get there. Here's the shortcut. Suppose we have a number graph on the complex plane. If I want to express this in polar terms, I need to find r and theta in terms of u and v. Similar to the last set of notes, we can express this relationship in terms of sine and cosine. If we substitute, we can rewrite this complex number in terms of r and theta. We can factor out the r to get the polar form of any complex number. This has a convenient abbreviation. If we take the letters c, I, and s from the expression cosine theta plus I sine theta, we get r theta. Remember that cis is not a function, it is an abbreviation. We'll use that right here. This abbreviation makes it easy to convert a polar complex number into a rectangular complex number simply by expanding. We can use a similar process from last time to convert this rectangular form complex number into a polar form. Now we get to see the benefit of using polar form complex numbers. It makes arithmetic very easy. Suppose we have two complex numbers in rectangular form. I'm going to declare variables of r1 and r2, theta1 and theta2, to express the polar forms of these. To multiply two complex numbers, this is what we had to do before. Then we had to simplify, and it got old fast. This is how we do it in polar form. If we refer to these 2 points as z1 and z2, then their product is simply this. We multiply the r's, and we add the angles. Similarly, if we wanted to take a quotient, we would have to multiply by the conjugate. This could get ugly fast. Fortunately, in polar form, it's very easy. We divide the r's, we subtract the angles. To really see this in action, we need an example. Multiply the r's, add the angles. To divide, we divide the r's and subtract the angles. To deal with example 8, it looks like a mess until you realize that these angles are the same, meaning that this is simply cis form, where theta is pi over 3 on one end and pi over 6 on the other. Again, we multiply the r's and add the angles. Our final result is something known as DeMoivre's theorem. It's about raising complex numbers to exponents, and it uses polar complex form to make it, again, simple arithmetic. Suppose we have r cis theta. Based on our multiplication rules, we can find z squared. This is simply z times z, which is r cis theta times r cis theta. Recall that all we did was multiply the r's and add the angles. We can do something similar with z cubed. Once again, we multiply the r's and add the angles. DeMoivre proved that this holds in general, no matter what the exponent is. Again, we multiply the r's n times for this arbitrary exponent, and we add the angle n times for this arbitrary exponent. This makes things very nice. When we raise to the sixth power, it works the same way. To fully simplify this expression, we can use a coterminal angle to 4 pi, since 4 pi is a little bit out of our normal range. Thanks for watching.